All right, guys, we're going to look at problem number 7 on number 5.4, just looking at a person on the top of some sort of cliff here that you'll see is 50 meters above the ground, and they're bungee cording. This is not two different people. This is the exact same person at two separate times. Now, we are going to do this problem in a slightly different way in the future. So heads up, I'm going to try to keep it as close as possible to how we're going to do it in the future. But this is going to be slightly different, like I said. So again, we have a person starting up here, 50 meters above the ground there, and then they fall till they are 12 meters above the ground, and the bungee cord here is extending while that happens. It tells us that the problem has a potential energy of 34,300 joules and a mass of 70 kilograms. There's one other number that I haven't written down, and that is that the string, or the bungee that I was talking about, is 15 meters unstretched, which I'll address in just a second. So the way that you should usually do this is, so you see it in the future, you should look at mechanical energy initial and mechanical energy final, because in this particular case, these are conserved. That's just so you know for the future. I'm not going to do that quite right now, but it's pretty darn close to that. So we are told the total potential energy right down here, like I said before, is 34,300. And we don't have kinetic energy up here or at the bottom, so we can basically just say potential total is going to equal the gravitational plus the elastic. My apologies here. Elastic potential energy. And we're using this to try to figure out what the heck K is. All right, so we can look at either spot. We can look up here, or we could look down here, except this is the one we want to use because there's no kinetic energy, there's no elastic potential energy on top, so we should look right down here. So all we're going to do is we're going to take each of those equations and expand them. I'm going to shorten that to potential T, and that's going to be mass times gravity times height plus 1/2 K delta X squared. You might have done this in separate pieces. This is the general gist. So we already know that number. We know that number. Obviously, we know G. Height is the height here because that's when we're looking. So that should be, height should be 12 meters for this particular problem. And for everything else, we're pretty good. We just need to know delta X. Now, I'm going to tell you the answer for delta X first. It's going to seem a little bit weird, and then we'll go over it. The answer to delta X is 23 meters. And the reason why is because we see up top here that they go from 50 meters down to 12, which means they have moved from there to there a total of 38. Okay, so the reason it's 23 is simply you'll remember that that string is 15 meters unstretched. So until it gets to the 15th meter, it's not going to stretch, meaning all I need to do is take that 38, subtract off the 15, and that tells me that it's going to stretch a total of 23. So now all I need to do is algebra and plug numbers in. So I'm going to subtract MGH on the other side, multiply everything on both sides by 2, divide everything by delta X squared, and that should give me K. So let's go ahead and plug those in real quick. 2 times 34,300 joules minus 70 kilograms times G times the 12 meters, like I was saying. Make sure you put closed parentheses on that, divided by 23 meters squared, and if done correctly, that should end up as 98.7, and those units are newtons per meter because it is a spring